is in continuation to the previous one, that where we had discussed the voltage regulation, how it can be calculated, and the basic requirements of the for the calculation of the voltage regulation. We needed the resistance of the armature, open circuit test, and the short circuit test. So those were discussed before. One of the methods, synchronous impedance method, has been discussed before. Now today we'll be discussing the remaining two ways of calculating the voltage regulation. So the topics to be covered today are the determination of the voltage regulation by ampere turn method or the MMF method, and the zero power factor method or the Pottier method. So what is the ampere turn or the MMF method? Ampere turn method of finding voltage regulation considers just the opposite view to the synchronous impedance method. It assumes that the armature leakage reactance is to be added to the armature reaction. So XL has to be added to XAR, that is the armature reaction drop. So this method assumes that change in the terminal potential drop on the load is entirely due to the armature reaction. And then the same two tests, open circuit test and the short circuit test, are required as for the synchronous reactance type of method, but the interpretation of the results will be different. So under short circuit condition, the current lags by 90 degree, assuming that Ra is equal to 0, the armature resistance is 0, and the power factor is also 0. Hence, the armature reaction is entirely demagnetizing to the main field. Since the terminal voltage is 0, all the field ampere turns are neutralized by the armature ampere turns produced by the short circuit armature current. So this is your ampere turn method for the zero power factor. Now suppose the alternator is supplying a full load current at normal voltage and zero power factor lagging. Then the DC field ampere turns will be required to produce the normal field voltage. If Ra is taken into account, it has to be V plus IRA cos phi at no load, those to overcome the armature reaction. So for the armature reaction, the DC field ampere turns required is V plus IRA cos phi, or if you neglect the Ra, that is the armature resistance, then it will be only the normal voltage. Over here in this phasor what we have drawn, this AO is the ampere turns to produce the normal voltage V at no load, and OB1 is the field ampere turn required to neutralize the armature reaction. So then the total field ampere turns required will be the phasor sum of AO and OB1, that is equal to over here AB1, because it is directly in addition to it. Hence your total field ampere turns will be AB1. Now AO can be found from the open circuit test, while OB1 will be found from the short circuit test. So the use of the DC quantity field ampere turns as a phasor is perfectly valid in this case, because the DC field is rotating at the same speed as the AC phasors. Because when we rotate the turbine is rotated at the synchronous speed, hence it is rotating at the same speed as the field produced by the armature. So for a full load current of zero power factor lagging, the armature ampere turns are unchanged. Since they aid the main field, less field ampere turns will be required to produce the given MMF, because it is the zero power factor leading now. So it is just in the 180 degree phasor difference to one which was required for the lagging power factor. Hence it will be just the opposite. So the total field ampere turns required will be now AB2, that is equal to AO minus OB2. So only AB2 field ampere turns will be required in case of the leading power factor. So B2O is the field required to neutralize the armature reaction. Note that again AO is found from the OCC test and B2O is found from the short circuit test. Now between zero lagging factor and the zero leading factor, the armature MF rotates through 180 degrees. So at unity power factor, the armature reaction will be cross magnetizing and therefore OB3 will be drawn in just perpendicular to AO, and AB3 is the actual field ampere turns required in magnitude and direction. Now over here we have drawn the vectors which shows this circle where the variation of the field takes place for the lagging power factor and the leading power factor. You can see B1 and B2 both. So B1 is in the forward direction, that is for the lagging power factor, and B2 is OB2 is for the leading power factor. So the red semicircle shows the variation of the field ampere turns for the different power factors, and B3 OB3 was the field ampere turns required to neutralize the armature reaction at 0 power factor. So this is just the half of the two sides of the semicircle. So this is at 0, OB1 for the lagging power factor, and OB2 is for the leading power factor. So now, considering the different power factors, if the power factor is cos phi lagging, then phi is laid off to the right of the vertical line OB3, and the total field required will be AB4. That is this first one. The phi is the lagging one. If it is the leading one, it will go to the figure B, and now the field ampere turns will be required as AB5. So now we'll come to the actual current diagram. Now usual case is the lagging power factor. That's the reason we have taken phi as lagging over here. So the AO represents the field current to produce the normal voltage V at no load. Then OB is the representing the full load current under short circuit condition, and the resultant field current will be your AB, that is the total field current required for the balancing of the armature reaction. So the phasor AB represents the field current required for demagnetizing and to produce the voltage drop, either V plus IARA cos phi or only V if you are neglecting the armature resistance. Now what is the procedure for ampere turn method? We have got the OCC and the SCC characteristics. So the alternator is supplying full load current IA at operating voltage V and power factor cos phi lagging. So the procedure for finding voltage regulation for ampere turns method is as under. From OCC we'll take the field current of OA. So OA is required, the field current required to produce the open circuit voltage V, and the field current is OA. Now from the short circuit test, this OC is the field current required for the full load armature current to flow under the short circuit condition. So we get this OC from the short circuit test, and this angle 90 plus phi is for the lagging power factor load. So the voltage, open circuit voltage E0 corresponding to the field current OB on OCC is the no load EMF. Okay, so this is your E0, that is because this OC has been added over here. So this total current OB is the value of the field current which is required to produce the no load voltage E0. So this method gives a regulation lower than the actual performance of the machine. Hence it is known as the optimistic method. Now we'll come to the last method, that is the zero power factor method or the Potier method. Now here we are going to separate the armature leakage reactance drop and the armature reaction effects. So this will give a better result as compared to the previous two methods, that is the ampere turn method and the synchronous impedance method. So the experiment data required is the no load curve and the full load zero power factor curve instead of the short circuit characteristics. So it is known as the wattless load characteristics because the load will be at the zero power factor. Now it is the curve of the terminal volts against the excitation when armature is delivering full load current at zero power factor. So the reduction in the voltage due to armature reaction is found from the above characteristics. Second, the voltage drop due to the leakage reactance it will be the Potier triangle and is found from the both. So by combining these two, E0 will be calculated, and if the drop due to resistance and leakage reactance is added to V, E can be also obtained. So if the drop due to armature reaction, assuming lagging power factor, is further added to E, then E0 will be obtained. So here is the curve. Now here you can see you have got this no load curve, that is the open circuit characteristics, that is OK, and this OC is drawn in tangent to the no load curve. This AB curve is the actual load curve at zero power factor. So at zero power factor, how do we calculate it? There are different methods how you can load the generator with the zero power factor. We'll discuss those methods, but practically the last one will be applicable. First we'll discuss the method. So if a similar machine is available, then the motor can be driven at no load as a synchronous motor, and that will be practically zero power factor to obtain the zero power factor lagging curve, that is this AB curve. So or we can load the alternator with the pure reactors, that is non-inductive, the resistance will be 0 and it will be a pure inductance. So that will be the pure reactors, so that it gives you a 0 power factor lagging. Or we can also do apply this in the labs by connecting the alternator to a 3-phase line with ammeters and wattmeters connected for measuring the current and power, and by adjusting the field current such that the total wattmeter reading is 0. Because this is a 3-phase method, so 2 wattmeter method will be used, and 0 for the measuring of the reactive power. Your W1 should be equal to minus W2, so that W1 plus W2 is equal to 0. So you have to obtain W1 should be equal to minus W2, so that your W1 plus W2 is total 0. That means there is no power being consumed by the reactive loading, and that will be assumed that the alternator has been loaded at 0 power factor. Full load will be obtained from there. So point B was obtained in this manner when wattmeter was reading 0, that is this point, and point A was obtained from the short circuit test with full load armature current. So we got this OA point, and then we join the AB curve so that we get the complete graph of the full load curve at 0 power factor. So OA represents the field current, which is equal and opposite to the demagnetizing armature reaction, and for balancing the leakage reactance drop at full load. Now we'll try to draw this Potier triangle, that is your H, B and D. So from B we'll draw BH will be drawn, which is just for the no load voltage, or parallel to OA this line is drawn where the full voltage is obtained. So the second point HA will be, HD is drawn parallel to the initial straight part of the no load curve, that is this tangent. We draw it with the initial slope, and therefore to parallel to OC we get the same line as your HD. Now D on the no load curve corresponds to the point B on the full load curve for the 0 power factor. So the triangle BHD is known as the Potier triangle. This means this B is the full load curve point, H for the voltage under no load, that is this curve is extended, and parallel to OA we cut this point BH. So BH is equal to OA, and this D is drawn, D point is taken as the perpendicular drawn to this HB, and we get this point as D. So D is the point on the no load curve corresponding to the point B on the full load curve. So now this triangle is constant for a given armature current. So this, if you take any point on this curve, full load 0 power factor curve, and you draw this triangle, everywhere you will get the same triangle. So you can draw the line DE which is perpendicular to BH, and the length DE will represent the reactance drop, and the BE will represent the armature reaction drop, which is having the demagnetizing effect at full load condition. So we have got both the reactance drop and the armature reaction drop. So EH is for the balancing of the armature reactance drop, DE. Now we'll have the vector addition of the uh, full load voltage and the voltage drop due to armature leakage reactance alone. So you will get the curve as DF. So D and F, which is drawn in parallel to this to calculate the value of the E. So we'll get the induced EMF under just the leakage reactance being considered. So when you have got this armature reactance drop also being considered, that is equal to this BE, and when that is added we get the E0, that is your no load induced EMF. And at the bottom we can have this curve as 90 plus phi, which is in parallel to the no load curve. This C in parallel to this angle is 90 plus phi. So you will get this circle which we have discussed before, that how that circle is being obtained for different types of the power factors. If it is 90 minus phi, the current is leading, so you will get this OFG on the other side of the line, and you will get the induced EMF. So the percentage regulation can be calculated as E0 minus V by V. Now what does this Pottier triangle say? That is, this is your phasor diagram, which is your normal phasor diagram which we have drawn before. This is your terminal voltage V, current is lagging by an angle phi, IRA drop is in parallel to the current, and this is your reactance drop, and this is your armature reaction drop. So when you have got this E which is added to this RA and XL drop, that is the reactance drop, you get the induced EMF, and the field current will be just at 90 degrees to it, and you will get this OF, which is the field current requirement for the production of the induced EMF E. And when the armature reactance drop is added to it, then we get the no load EMF being induced, and this OG is 90 degrees to this OL curve, that is E0. So OG is the field current required to produce the no load induced EMF in the armature. So you have got this OG field excitation for E0, and the vector E0 is lagging behind by 90 degrees to OG, and therefore DL represents the voltage drop due to the armature reaction. So now in this method we have considered both the reactance drop and the armature reaction drop. So basically what are the procedures to be followed for this Pottier method is, we will be given the V terminal voltage per phase, then we will calculate the armature leakage reactance and hence calculate the reactance drop, then adding the reactance drop, and if you consider the armature resistance, then IRA drop also, that will be added to V to get the voltage E. Then to find from the no load curve field excitation for voltage E, that will be IF1. Further, field current IF2 necessary for balancing the armature reaction is found from the Pottier triangle, and combining both the field currents as in the ampere turns method, we get the total field current, and from the no load curve the EMF corresponding to this gives us the E0, that is the induced EMF at no load, and hence the regulation can be found. So this is the best method which considers both the reactance drop and the armature reaction drop. Hence we can go for the zero power factor method if we want the exact calculation, or if some approximation can be made, then depending on the availability or depending on the requirement, you can go for the ampere turn method or the synchronous impedance method, which we had discussed last time. So thank you.